Come on, come here, bud. Come on. You freaky dog. I don't need to analyze every word that comes out is a lie. Make it look like you're so ice, ice, ice. You won't make it to the finish line.
Welcome to another Sunday Toolbox Tech Talk.
Never mind, unpredictable. Feet eye off the ground, you ain't no one. You a star, blow it up like supernova.
It's always party time here at the Smart Energy Lab.
Sharing secrets, you wish really was part your life. Basic bullets, with my bullets. Does your wifey know you're begging for my notice? Promise you're the same.
Well, no, you haven't tuned to the wrong channel. It is actually Toolbox Tech Talk, not some crazy rapper smoking out. Hey, good to have you all here again. It's great to see the audience turning up every Sunday, 1 p.m. Cool, thanks for watching. And I can see already I've got a few of the regulars in there. G'day Charles from Waiheke. Go Waiheke. Beautiful little island just in the harbour of Auckland. Fantastic place. Have some fond memories. Little trips out there. You know, I grew up in New Zealand, so spent a bit of time in Auckland. Wellington, my homie. Yay. G'day SW from Wellington. Good to hear you. We'll see you there. And Martin from Bellevue, WA. I guess it's still early morning over there with that 3-hour time difference. Okay, so what do we got today? What do we got? Apart from a whole lot of smoke in the studio, which hopefully will diminish soon. Just checking all my things here. So I've got a little program for you today, and we're going to be talking about a bunch of things, but the highlights is really trying to break some of the myths around solar, and you can throw some in there too and see if they're myths or not in the chat. So I really like to get a bit of interaction going, so feel free to ask questions or make comments. So first up, this is actually the last Toolbox Tech Talk for 2024. Don't you worry, I'll be back again in January, the 5th of January. I'm not going anywhere, so that's cool. I want to do a few promos here. One of them is, of course, for the Smart Energy Council for their Smart Installer program. Now, they're changing the program. It's going to be a fee for standards, but still free to join. So you can join Smart Installer program for free. You do, as part of that free joining fee, or joining, so there's no fee, that free joining process, you get a copy of 4777 Part 1. So ASNZS 4777 Part 1, the standard for inverter systems, and that's free. But if you want to get access to a bundle of 9 essential standards, it's going to cost you $99 plus GST if you're in Australia. One of the big bonuses of being a member of the Smart Installer program too is you get access to a whole lot of training which has CPD, continuous professional development points associated with it, over 170 currently. So if you're one of those accredited with Solar Accreditation Australia and need to keep your points up, you've got to get 100 points every year, you can get them as part of that Smart Installer program. So that's pretty cool. And of course, there's going to be links to some really good content. So there you go. Now, I've got a bit of a news spot here. So my news spot is a new thing I'm doing. I'm just kind of checking out what's happening, interesting, exciting things in the world of solar and batteries, renewable energy, smart stuff. And there's just a couple of items, or actually 3. I just Googled to see how big, solar utility is getting, and I came across this one in Panama, which is a country of a population of 4.5 million. That's less than you guys, New Zealand, just building a 530 megawatt solar farm. Yeah, with the help of Power China. Wow, 530 megawatts for that little country. That's a big jump. Other exciting news, if you happen to live in the UK, is your relatively new Prime Minister is promising to make millions of cheap loans and grants for solar and batteries. Yep, millions. So that's a big program. And it's because they want to get to zero carbon electricity by 2030. So the UK, which isn't a real sunny place, but, it still has sun, wants to get to zero carbon electricity by 2030. Wow. Bye-bye nukes. What else is up? Oxford PV. Now, if you haven't heard of Oxford PV, and neither had I until very recently, but I had heard of perovskite. Now, if you don't know what perovskite is, it's a photovoltaic material that's been in the sort of offerings of promising big things, but it's never really been commercialised and hasn't got to that stage where it hadn't got to the stage where you could actually go and buy panels and stick them on your roof. But now Oxford PV have just released the first commercial tranche of what's known as tandem cell perovskite. Now, perovskite is got a lot of advantages over just pure silicon. It's really low cost to make. It's made at low temperature. I mean, we're talking you can sort of home bake it really. It's not using esoteric materials, so it's relatively low cost input, and it can be made super thin, like 500 nanometers thick. That's almost invisible. So incredibly thin coatings still produce, and they have electricity from sunlight, and they have a wide band sensitivity. That means they capture more of the visible spectrum from UV through to the red, from the violet through to the red spectrum. And as a result, they have really high efficiencies. Now, at the moment, they're still only in the sort of high 20s in research labs, but they expect to get into the 30s. So that's been a bit of a challenge for silicon. Silicon's always had a theoretical maximum in the high 20s, but perovskite looks like it can go a lot further and be cheap. So that's a big plus. So, they're actually selling solar panels. They're doing a utility scale program for somewhere in the US at the moment. So there you go. Okay, what are we looking in the chat here? Gordon says single axis trackers for ground mount. Look, I've had a varying opinions on solar panel tracking systems. So back in the day, when I'm talking like 20 years ago, they were rather exciting because solar panels cost an enormous amount. We're talking $10 to $20 a watt for solar panels. And so you wanted them to work as well as you could. So people were putting in single or dual axis trackers to get the most out of them. But there was a very hit and miss in terms of their reliability. Some systems really just couldn't hack moving panels out in the weather for any length of time. So there's a lot of failure, particularly with the dual axis trackers. But panels got cheaper, and they got really cheap, and they still are really cheap. And as a result, trackers didn't really offer a big financial advantage. They still offered a bit of a space advantage. They didn't you could get more performance off a smaller area. But of course, you wouldn't put it on your roof. You can't track things on your roof very easily. So you needed to have a ground mount system, and that would also limit its application. And utility solar was pretty fixed on, funnily enough, no pun intended, fixed solar arrays. But what's happened is single axis tracking has got really low cost. And I've got a couple of utility trackers here from Arctech Solar. I might do a little piece on them once we put the new ones in. They're pretty amazing. I mean, 90 metre long torque tube that rotates from east to west every day. It can withstand tremendous winds. We're on top of a mountain at 700 metres here. We get some big winds. So they actively protect themselves by moving into a stow position when the wind speeds, I think, over about 16 metres per second for the trackers I've got, but their new ones go up to, I think, 18 or even 20 metres per second. So very reliable. But what the trackers give you is a higher production per acre or per hectare. And that's because that's one of the reasons they've come back into favour for utility solar is the cost of land. So even though solar is really cheap, land is another cost. And you also get, and this is a big bonus, a very flat production curve. What I mean by that is you don't just get a peak in the middle of the day as you do with fixed equator-facing panels. You get a long, slow rise. Not slow rise. You get a fast rise in the morning. So my panels in summertime, as soon as the sun hits them, they're almost at full power. So you get this long, flat generation. So you get more kilowatt hours per day and you get less peaky production, which is great for selling electricity into a wholesale market. Martin says, I've had tracker experiments running for the last 3 years, had to replace the motor 3 times in that period. Yeah, I think you reinforced my experience too with small scale trackers. But really they're a great hobbyist thing if you're into it, just watching stuff move around. But yeah, commercially for domestic and small commercial, it's probably not viable. It's more of the utility market. But yeah, Martin, thanks for raising that. Okay, so, actually it was Gordon who raised it. And SW says, is that due to wear and tear on them or poor quality motors? Well, basically you're taking something that has almost no maintenance, a solar panel, and you're adding something that moves and has gears and has to withstand stresses that are dynamic. And it's a tough call. So yeah, whereas the utility trackers I have here, they have this enormously long and solid torque tube. The panels are actually dynamically supported by shock absorbers. So that means they can actually absorb a gust of wind and move, and then sort of move back like your shock absorbers smooth your ride on your car. And they're driven by a slew drive, which is an incredibly low gearing system. I mean, the drive motor is 110 kilos. I had to, with 4 people, lift it up on top of the mounting system. So it's really, really tough. And being a slew drive, it has like a worm drive mechanism. It only has an 83 watt motor to move tons of solar panels. It's amazing. There you go. But like I said, I will do a little special on solar trackers, maybe when we get the next tranche of them installed. Okay, so yeah, I see Martin says he found one of the actuators had leaked water. But like I say, they're a great hobby thing. Now, let's talk about those 7 myths. Now, I've got a little presentation. Oh, actually, before I do that, I was going to show you hang on, where is it now? I was going to show you the website for Smart Installer program, just so you knew what I was talking about. And so if I bring that up there, here we go. Okay, so that's the Smart Installer program from the Smart Energy Council. So you can just go to smartenergy.org.au and under programs, you'll find Become a Smart Installer. So yeah, access to standards and CPD points is what it's all about. The other one is I like to give a little plug to Solar Cutters. You probably see my T-shirt here. Cutters have been a big supporter of my channel. Really appreciate some of the merch they've sent me, but also the ability to communicate with their audience. Now, there's literally thousands of members of Solar Cutters. It's a industry group. Well, what a little question there. It's an industry body. It was founded back in 2017 as a Facebook group, but it's become so much more than that. And it's a great peer support and helps Facebook page for the solar industry. Almost every day someone's asking a question, and it's very supportive. There's not like everyone telling you you're an idiot for asking a dumb question. People understand that if you're a bit new to the industry, you've probably got a bit of a steep learning curve. So yeah, Solar Cutters, thanks for that. And they also have some great content on their website, and I'll just scroll through it a little bit, show you, where are we? Oh, I haven't got it there. It's offering training discount for training. So they've done some partnership deals with GSES, for instance. You get 10% off their courses as a member of Solar Cutters. With Southwell Solar Training, you get 30% off Pat's courses. So Pat Southwell, who's a licensed electrical inspector here in Victoria, he's doing a lot to help train the industry. So yeah, big ups to Pat. And of course, the Solar Training Centre, who've been around a long time, they started off in Adelaide, but now they're in other states in Australia. They're offering up to 60% discount. Now, that's actually because they allow you to access some of the state-based funding, I believe, for different training courses. So yeah, the Solar Training Centre, really recommend them. So there you go. That's a little bit of promo for those guys. Okay, so just getting on to 7 deadly, not 7 deadly sins, 7 myths of solar. You may have seen the slightly silly promo that I sent out via my direct messaging, and it's got me dressed up as one of the dudes from Mythbusters. It was actually because I did a duo with Jeff Stapleton from GSES, and we pretended to be the two guys from Mythbusters busting some solar myths. But I thought I'd just run through. These are fairly basic ones, but they still have a bit of leg to go. Some people still think these are true. These things that you can't do. So this is all about things you can do that you thought you couldn't do, or if you couldn't do it, if you could do it, it wasn't a good idea. So there we go. The 7 myths. So let's look at the first one, east-west arrays. Now, what I'm talking about there is on a single tracker. Now, remember, inverters have maximum power point tracker inputs. That's so they can operate the array at its most efficient voltage and current. And I think I've mentioned this 1,000 times, but it's an Australian invention. Stuart Watkinson, back in 1983, was the first to commercialise an MPPT. How's that? Wow. And every inverter in the world now basically has one. Single axis, a single MPPT, but with 2 parallel strings connected to it. And of course, as 5033 states, once you have parallel strings, there must be the same number of panels in each string. So in this case, 18 panels on the east and 18 panels on the west. And all of those must be in the same orientation in each parallel string. But the strings can face different directions. Now, is this a good idea? A single tracker? You might go, well, hang on. Let's say the sun's in the east in the morning and those panels are really pumping hard, and the panels in the west in low irradiance, not shade, but basically not direct sunlight, just indirect irradiation, they're going to be working much weaker. But because it's a parallel circuit, the currents can add together. So it's basic electrical theory there, Kirchhoff's current law. And so, yes, the currents can add together, but what about the voltage? Is there going to be a voltage mismatch? Well, it turns out by a kind of a fluke of physics that 2 phenomena counteract each other out when it comes to voltage. So in the east side in the morning, the higher the irradiance, the higher the voltage. But at the same time, the higher the temperature, the lower the voltage. So solar panels have a negative temperature coefficient, but a positive voltage coefficient for irradiance. And the two cancel each other out. When I say cancel, that means that when there's a change in temperature and irradiance, in the way that normally happens when the sun shines on something. So the sun shines on the panels, there's more irradiance, and they start to heat up. That stops the drift of voltage. Whereas the panels on the western side, which are in lower radiance, so lower radiance means lower voltage, but they're cooler, which means higher voltage. So once again, the two phenomena cancel each other out. Now, this is not just me dreaming up this idea. Both SMA and Fronius have produced white papers, academic white papers with test results showing this to be true. So yes, you can parallel east and west or north and south or any combination of orientations onto a single MPPT, and there's no problem in terms of voltage mismatch. The other question is, would you do it? Well, the evidence from the white papers from SMA and Fronius show that there's less than 1% difference between a dual tracker, dual input tracker with separate trackers for each string, as opposed to paralleling two strings together. So it's less than 1% difference. So really it's insignificant performance difference to have a single MPPT with two strings on it. The other question is, what's the other benefit of doing east-west? Well, the other one is you're actually producing less kilowatt hours per day than if you faced all your panels towards the equator. Now, because we're on YouTube, there's people watching from the Northern Hemisphere as well as the Southern Hemisphere. So I'm trying to avoid saying things like your panels should face north, because of course everyone in the Northern Hemisphere is going to freak out and say, Glenn, you've got it totally wrong. They should face south. Well, equator facing is the more uniform term. So if you had your panels facing towards the equator, they would produce more kilowatt hours than facing east and west. But for many applications, there's more useful kilowatt hours, more useful as in self-use of the energy. And that's because an east-west array particularly will have a very flat production curve. So the eastern panels will peak in the morning and the western panels will peak in the afternoon, and the sum of the two in the middle of the day, which means that you get a long, flat production curve, which is great for self-use of solar rather than having a big spike in the middle of the day with an equator-facing array. So there you go. East-west, it works, it's allowed, it's compliant with the standards, and there's definitely some economic benefits for maximising self-use. That's the first myth busted. Feel free to ask questions as we go. And I usually do a little drawing to explain some of these things, and I just realised I was going to draw something to explain this one. So let me just do my little overheady thing. See if I can get it up here. All right, where are we? Overhead. Okay, it's my little pen. Right, so this is a little graph of the production of a PV array that's equator facing. That's a typical bell curve that you'll get. So this would be solar noon. You've got to remember that the sun peaks at solar noon, not clock noon. So here in Melbourne, we've got daylight saving on. And that means we're an hour away from a normal midday point. But also, because we have time zones in Australia, as we do everywhere in the world, we're actually about 25 minutes behind the sidereal time, which is, the sun's actual position. So solar noon right now in Melbourne's about 1:25 p.m. There you go. So there's your peak, and you might say that's producing that's 100% of the production peak, and that's a equator facing array. Of course, the tilt angle will determine the seasonal variation as well, but we'll get onto that. But if you've got an east-west array, you'll end up with, that'll be your east, and this will be your west. Okay, and so the sum of the east and west together will kind of be a longer, flatter curve. So not as peaky in the middle of the day, but producing more usable energy for self-use during daytime. And that's what we're on about here. Now, it has an even better match when it comes to commercial solar, because commercial solar, or I should say commercial loads, places that work during the daylight hours, will often have a load curve that looks like this. Like nothing much at nighttime. They turn the lights on. Everything goes well all during the day, and they turn the lights off. And so they have a very flat consumption profile. And so this east-west orientation better matches self-consumption of renewables. There you go. Okay. Back to my myths. So oversizing of a PV array. Now, just a bit of terminology here. In fact, this is a slightly older presentation, so some things have changed. I have this terminology called the silly CEC guidelines. The CEC, the Clean Energy Council, no longer manage accreditation, and their guidelines not relevant, but Solar Accreditation Australia has taken over accreditation for solar installers in Australia. So it's SAA now. I should change this slide sometime. But they've had to continue these silly guidelines because they're locked in with a federal government requirements, the Clean Energy Regulators requirements for compliance to the small-scale renewable energy scheme, which is what people call the solar rebate, which actually is a certificate program for renewable energy. Anyway, that's a long-winded way of saying the guidelines state that the maximum amount of PV can only be, it's actually usually stated in the inverse, but they state in the guidelines that the inverter must be at least 75% AC output power of the peak watts of the array. Now, if you do the inverse of 75%, that's 133%. Oversizing is the maximum to be compliant with the SAA guidelines for systems without battery storage. And that's a very important point. Systems that don't have battery storage attached have to comply with that requirement in Australia for access to government rebates. It's got nothing to do with safety. It's got nothing to do with electrical regulations. It's really just an economic regulation here in Australia. But a lot of people kind of get stuck in their head that somehow you can't go over 133% extra PV. And others would even say, why bother? Why would you have more PV power than your inverter can convert? So the array might be a 6.6 kilowatt PV array, but you've got a 5 kilowatt inverter. And you might go, well, I'm basically wasting a whole lot of my solar. So that little graph is showing the notional lost production. But the reality is that a solar panel is tested under very unusual conditions. It's tested under 1,000 watts per square metre of irradiance, which is kind of typically midday sun, but at 25 degrees Celsius cell temperature. Now, you might think, well, that's kind of a nice, comfortable temperature, you know, on a beautiful New Zealand autumn day. Well, in Australia, it depends where you are, what the temperature will be like then. Well, the reality is that solar panels heat up just like a metal roof. So if you put 1,000 watts of solar radiation onto that solar panel, the cells will be up to 30 to 35 degrees hotter than the ambient temperature. And so they'll be hot and they'll derate. So the reality is that solar panels rarely ever will produce their rated power except in really cold conditions, cold and sunny. So somewhere like Antarctica, beautiful, you'll get some fantastic performance out of your solar panels. You'll probably even get more than their peak watt rating because it's a linear negative slope. So that means the colder you go from test conditions, the higher the performance. But yeah, oversizing is a good idea to accommodate that loss of production that's going to occur due to just the panels heating up. But the other one is that every day isn't a sunny day like this, unless you live in Queensland. So if it's an overcast day, having that extra headroom of PV power means that you can still produce more useful kilowatt hours in a day, even without hitting the maximum power of the inverter. So yeah, overpowering, great idea. And in a way, you're not wasting anything and you're not damaging anything. There's no sort of overloading of the inverter as long as you stay within the inverter's maximum recommendations for oversizing of the PV array. There are some practical limits. You can't exceed the current ratings for short circuit. We'll talk more about that in a second. Also, if you excessively oversize beyond the manufacturer's recommendation, you probably have no warranty, and that's because you're putting a bigger thermal load on that inverter and it may not last the warranted period. So there are those limitations. Okay, I'm just checking the chat here. Can't see any questions. Quiet bunch. All right, so what about with this overpowering? Is it going to blow up the inverter? Like, you know, you might see a panel puts out 20 amps of operating current, IMP, but the inputs can only accept 15. And you might go, whoa, does that mean I'm going to damage my inverter by having 20 amps coming out of my solar panels and the inverter can only receive 15? Well, it turns out that inverters are actually smart loads. Solar panels don't push current into the inverter. The inverter literally, well, not literally, figuratively sucks current from the PV array. It basically determines how much to draw. So it's a smart load. It can change its input impedance to determine the amount of current and voltage that it wants. And so if it's got a maximum input rating of 15 amps IMP, it will limit the array to 15 amps, even though the array could potentially produce more. However, there are some hard limits, and that's what we call the ISC ratings for MPPTs, the short circuit rating. So, for instance, if the inverter were to fail internally, short-circuited, and these things do happen, capacitors go short-circuit or some other tragedy inside the inverter, the current from the array will now flow at its ISC through the input terminals of the inverter. And so the inverter's in no way controlling that current. And so you have to stay within the ISC rating of the inverter so that you're not thermally damaging it, so the plugs don't burn off and live wires drop onto the floor. So that's the other consideration. As long as you don't exceed the ISC input of the inverters can certainly happily limit the current. Okay, just looking for any comments here. Okay, nothing there. Cool. So that's 3 down. Here's number 4. Now, once again, this is a bit of an Australian thing. STCs, which are small-scale technology certificates, which is the certificate scheme in Australia for under the small-scale renewable energy scheme to encourage systems up to 100 kilowatts to be installed. In fact, it's 100 kilowatts of AC power, I should say, to be installed on homes and businesses. Now, I've heard people state, oh, you can't put solar panels on the south. Now, once again, this is a southern hemisphere view of the world, so facing away from the equator would be more technically correct for the whole globe. You can't put panels facing away from the equator because, you won't get any STCs in Australia. Well, that's not true. There is no orientation requirement for the creation of renewable energy certificates for solar in Australia. They can face any direction you like. The other one is, well, it's just not going to be worth it. It's the shady side of the house. Well, it's all about the pitch of the roof and your latitude. Those two things are the biggest factors. Now, just to use an example for Auckland, for instance, and using solar radiation tables that I have, for an optimum orientation, that means in the case of Auckland facing, not optimum, a suboptimum, but the ideal tilt angle of around about 23 degrees, facing south in Auckland, it would be better than a optimum facing system in Germany. So Germany at a latitude of somewhere in the 50s, 50 degrees from the equator, has a much lower amount of solar radiation compared to Auckland. And a south-facing array in Auckland actually will work better than an optimum-facing array in Germany. There you go. So it's all about where you live, your latitude, and the pitch of your roof. But the other thing to consider is that not every day is actually got pure sunlight. You must have some days which are overcast. And when it's overcast, you're only receiving indirect solar radiation. It doesn't actually matter which way you face your panels. If they're getting indirect solar radiation, south will be as good as north. It makes no difference at all. But there is one more advantage, and see if I can draw this one. Get my little drawing pad back up again. Here we go. So let's just draw a house in plan view. It's got a hip roof like this, and we'll say this is north here. And we've put our panels on the south side here. Now, of course, you've got lots of factors when it comes to where you're going to put your panels, but, and I should say, this is the note here, southern hemisphere. Can't spell sphere, there we go, southern hemisphere. The sun in a latitude like Auckland will, in the winter time, be rising somewhere like this. So this is winter, and going through a trajectory like this. So it's actually going to have pretty poor access to that south side of the roof, because the angle of the sun gets down to about only, I think about 28 degrees above the horizon. So if your pitch of your roof is 23 degrees, it's just going to skim across those panels. So it's true, in wintertime, those south-facing panels are not going to be doing much. But in Auckland, in summertime, the sun rises here. So this is the east. This is the west. And does this enormous arc right around to here. And also the time of day. So you're probably looking, I don't know, 6:30, bit of sunlight through to about 7:30 p.m. So you've got a really long day, and you've got sun in the morning hitting the south side of the panels before they even get around to the north. So not till the sun gets past this point here does the north even get any sun. And then in the afternoon, the reverse happens. You're now getting sunlight in the late afternoon onto the south side of the building. So what that means is that in summertime, those south panels are actually giving you a little boost at the beginning and at the end of the day. However, I'd still recommend putting panels in more optimum orientations if possible, but I sometimes refer to south as the new north because it's empty. Yeah, everyone sort of fills up all the good spots first, whether it's pool heating tubes or hot water services or a solar PV array, and then there's this empty south-facing roof, and you go, well, south in the southern hemisphere, it's empty. Let's use it. Every part of a building is potentially useful. Cool, there you go. All right, so we're up to... that was my little explainer. And my next slide is, where are we? Keypad. Is, gone too far. South-facing arrays, just done that one. Oh, yeah, shading. Okay, good. No, I haven't gone too far. Number 5. So number 5 in Myths of Solar. Hang on. I see a question from Martin before I move on. Martin says, solar charts show that at summer solstice, there are quite a few hours of sun from the south. Exactly my point. Thank you, Martin. So, and once again, if you happen to be in the Northern Hemisphere, just reverse all of these word orientations that we're using. Cool. And just out of interest, anyone from the Northern Hemisphere watching? I'd love to know where you're watching this from. Just type it into the chat. And Charles says, we did a system on the Chatham Islands, which is a very remote group of islands, part of New Zealand, actually, off the east coast of New Zealand. And at $1.37 a kilowatt hour, any surface is cost effective. So you're saying that the cost of electricity, wow, on Chatham Islands is $1.37 a kilowatt hour. I imagine it's a diesel grid, so yeah, it's the price of fuel is having a big factor in the price of electricity. So yeah, south actually suddenly looks very cost effective with that cost of mains electricity. So onto shading. Now, shading of an array is bad. That people sometimes say, oh, there's shade on my roof. My roof is not suitable for solar. What a shame. Well, there are many ways to deal with shading. And one way is actually having a string of panels, which gives you a relatively high string voltage so that the inverter can operate even when some of those panels are shaded. So built into every solar panel is a bypass diode. And the purpose of those bypass diodes is to partly minimize the impact of shading in a series string, but also to protect the panel from thermal overload. Now, once again, I might have to explain this little one with a drawing. So, overhead up here again. Okay, so let me draw a solar panel, and I'm going to draw some cells. So we're inside a solar panel are individual cells connected in series, and each cell will produce around about half a volt, and depending on the size of the cell, a certain amount of current. Big cells are up around 15, 20 amps at half a volt. But half a volt's pretty useless for trying to run equipment, so we connect them up in series to get a relatively useful voltage. So I'm drawing just dotted lines to mean more cells. Now this is what I'm drawing here is a 60 cell PV module, and I'll put it in a frame for you. So it's in a frame. So there's my 60 cell PV module. And what happens is there is effectively 3 submodules within a PV module, and between each of those is a bypass diode. Each of those submodules. It's built into them. It's actually a mandatory requirement under IEC 61730, which is the standard for PV modules, or test standard. Okay. So there you go. Now, when these strings of cells are producing current and voltage, they're reverse biasing this diode so it won't conduct. So under normal conditions, the current will flow through all of these cells, but nothing will go through the bypass diodes. So the bypass diodes are just sitting there doing nothing and they're cool. But as soon as you get a small amount of shade, now when you shade a solar cell, I'm shading it here, and we'll call this the gum leaf. Doesn't take much, just a gum leaf is fallen onto one of the cells. About 25% shading of the cell is usually enough. The cell will start to restrict the flow of current. Now, because this is a series circuit, if the weakest link determines the overall current. So without these bypass diodes, that little gum leaf will have the effect of not just this panel, but every single panel in the string. So you might have 10 panels in the string and they all drop down because of this gum leaf. So it's a requirement for solar panels to have bypass diodes that will conduct whenever this shade causes a restriction. So hence the name bypassing. And so the current will go through the bypass diode and then through the remaining unshaded parts of the module. So effectively we've got 3 independent generating components within one module. So 1, 2, 3. You've lost, when this bypass diode starts to conduct, you've lost the voltage contribution of this 1/3, but you've got still the same continuous current of all of the other modules. So in terms of shading, this is a very useful feature. I should point out the other reason for these bypass diodes is that shading, if it were to occur and the bypass diodes weren't there, this restriction here, this cell that's trying to impede the flow of current, will dissipate as heat proportional to the amount of current passing through it and the voltage across it. And what happens is that pretty quickly will dissipate most of the power of the whole array. Yeah. So if you've got a 6 kilowatt array, that one cell is trying to heat up to 6 kilowatts of thermal output, and basically it burns. So without these bypass diodes, you can actually have complete physical failure and even a fire in your modules. So there you go, pretty important. So coming back to that shading, that's one method that helps reduce the impact of shading. Another is individual, what's not generically known as MLPE, module level power electronics. And that includes microinverters, which go on each panel, or so-called optimizers, or DCUs to be more exact. So DCUs, or DC-DC power conversion units, they operate each module independently of every other module, and so do microinverters. And that means shading will have only the impact on the shaded module, but it will still continue to work. It won't stop working. It'll just work at a lower rate. So that's a really nice feature. So there you go. Shading can be dealt with design, with devices like microinverters and DC conversion units, or even in terms of how you lay your panels out. So once again, I'll probably draw a little example here. In fact, I can do it on top of this one. As you can see, this gum leaf shut off this one sub-module here, but imagine we have rows of panels that are orientated like this. So the sun's coming in on this side here, and so this array is starting to shade the one behind it. See that little bit of shade coming in there? So that small amount of shade might look insignificant, but it's occurring across the bottom of all 3 submodules. And even though it's a small strip, it turns off the whole panel. So shading on the short side of a module is generally much worse than shading on the long side. Shading on this side will still only affect 1/3 of the module's production. So there you go. Design matters. Sometimes that's about whether you put your panels in portrait or landscape orientation. Okay. West is best. I've heard people say west is where you should face your panels because that's where most of the loads are. Well, I think this person was someone from a hot part of Australia, which is air conditioning. So you've got a lot of air conditioning load, so why not face your panels to the west? It's sort of one of those things that's partly true and partly false. So really, when you've got no incentives to export electricity, i.e. feed-in tariffs, virtually, certainly in Australia and to most similar extent in New Zealand, not really worth it. You're not getting much more, you're getting much less than you would be if you use the energy yourself. It's all about trying to match your loads in real time with the solar production. And so if you got a lot of afternoon loads, so like air conditioning, then certainly biasing your production towards in the case of the Southern Hemisphere, towards the west. So I think that's true anywhere in the world, but there you go. So you want to bias it towards the west to get that peak in the late afternoon, which is when all the air conditioning loads are on. But you've got to also consider that there will be a higher temperature in the afternoon, and so there will be some greater thermal losses, but that's probably not as important as the benefit to self-consumption. So there you go. So west is best is not a generic truth. It's just about making your design fit the consumption profile as much as possible to maximize self-consumption. And lastly, on the little 7 myths, what is the optimum tilt angle? Now, you'll hear all sorts of rules of thumb, things like it should be the same as your latitude, or it should be the same as your latitude plus 23.5 degrees, or it should be perpendicular to the sun at the worst time of the year. Now, all of those things can be true in certain situations. So, for instance, if you're off-grid, the reality is that you have to consider what is the most difficult time with a solar battery system to generate enough solar energy to cover your loads predominantly. So let me explain this one with another drawing. Okay, so if this is our year, so we're looking at a year here, so once again, this is the Southern Hemisphere, so June is midwinter. So we'll call this winter here. And we've got December, we've got January, so our summer months. And so this is energy requirements on this side. So how much energy we need at different times of the year. And so if we look at a domestic residence, you might see a consumption that looks a bit like this. So it might have a little bit of a bump in wintertime because of the shorter days. More time spent indoors often means a bit more energy use, and maybe you've got some thermal heating as well. So that means there might be a bit of a bump in June. But if we overlay on top of that our solar production, and we might find our solar production goes, whoa, like this. So in summer, and this is our PV, and I should mark this, and this is our loads here. In summer, we've got a great surplus of energy, but in this design, we've got just enough to cover our loads in winter. So this would be what we call 100% solar fraction of your energy consumption. And this would be for off-grid, because the reality is in off-grid, it's use it or lose it. All this surplus in summer can't be exported because you don't have anywhere to send it. So this is an off-grid example I'm talking about now. I often show this to a customer when we're talking about sizing a system, and I say, even though it looks like you're wasting all this energy in summer, it's actually an opportunity to use energy. So some things that you might, for instance, in wintertime, you might use wood to heat the house and to heat water. But in summer, you've got all this surplus solar. Why not use electricity to heat water and run air conditioners to keep the house cool? So it's an opportunity for changing of appliance use based on seasons. Now, to get this kind of profile here, I'd be looking at June and saying this is the worst time of the year, June, and in terms of what they call the load resource ratio. So I'd try to orientate my PV array to give the best production in June. Now, I'm going to tell you this, and then I'm going to tell you why I don't do it. So it's kind of weird. So let's take a latitude of, so here in Melbourne, I'm at 37.5 degrees south latitude. So let's say Melbourne. So if you know what your latitude is, 37.5 degrees south of the equator. And the sun will be at a zenith of at midwinter, 28 degrees altitude. You can look this up in simple tables on the web to find out what the angle of the sun will be. So when the sun's at midday in winter, it's only just 28 degrees above the horizon. So the optimum tilt angle, if your sun is coming in, I'll draw it in red here, if that angle there's 28 degrees, right, and you want this to be perpendicular, you want the panels to be perpendicular, this has got to be the reciprocal of that, because, you know, that's going to be 90 degrees. So this is going to be, oh my gosh, 62 degrees of tilt. Pretty huge, isn't it? It's almost like, it looks like it's almost vertical. So if putting their panels at 62 degrees will give them the maximum, if they're equator facing, I should point out, the maximum performance in June. Now, having said that, this is all about treating solar panels as a precious resource. But if you've got low-cost solar, you can achieve the same amount of kilowatt-hour output just with more panels at a lower tilt angle. And so because of the cost of mounting systems, tilting panels is more expensive than laying them parallel to a roof. So generally, it just makes better sense to put more panels on and orientate them as best you can towards the equator, for off-grid this is, and just accept the angle of the roof. So if the roof is 23 degrees, put a lot more panels on. My favourite adage, by the way, is the solution is always more solar panels. There you go. Okay, so that's optimum tilt angle for off-grid. But what about on-grid? And I might come back to this example here. On-grid, there are a lot of other considerations. For instance, in this example, the panels are completely flat. And that will actually give more kilowatts of PV on a roof. So better coverage, even though it's not an optimum angle, you'll get more PV onto that roof. And so flat is not unusual in commercial applications, though it does come with a caveat, which is flat panels collect dirt really well. So they're going to need a cleaning regime. There are even automated cleaning machines, but sometimes it's done manually as well. So putting them flat can be just as good as tilting them. Once you start tilting panels, you've got to have inter-row spacing and therefore less panels on a roof. So there you go. Bit of a nightmare though if there's a fault to get to one of those panels in the middle there, but you know, that's someone else's problem after you've installed it, hopefully. No, you're covering it with the warranty. Okay, so that's the little 7 myths. There's so many more. I just thought I'd pick 7 of my favourite ones. Now, we've got a few minutes left, and I thought I'd just show you some things that have happened as a result of poor choice of plug and socket and also poor termination of plug and socket connections in a PV array. But maybe I'll sort of explain that one. I think I might run over time today. It's not a problem. I don't actually have a time limit other than just me, whatever I choose. But let me just get my little widgets out here. Here we go. Hang on. Just get myself set up here. And you want to see what I'm doing, don't you? I'm just preparing some plugs to show you a problem. Here we go. So these are very common connectors to have on the end of solar panels. And sometimes they're generically referred to as MC4s. Now, just wondering how much you can see, and maybe I'll hold it up a bit closer and refocus my camera. See if I can get a bit better focus on that. Wrong way. There we go. Okay, so that's what's commonly referred to as an MC4. But it's not an MC4. It's a work-alike. It means it's, in fact, I won't even use that term. It's a similar looking product. So let me show you a genuine MC4. It's a genuine MC4, and it has written on the side MC. Or is it that way around? There's a little MC in there somewhere. Now, they're very similar looking, except for the gland at the back. It's a bit bigger on the generic looking unit. So you might think, well, what's the problem, Glenn? Can't we just, it's hard to hold these in the right place. Aren't these interchangeable? Because it's a standard connector, isn't it? Well, actually, it turns out these are not standard connectors. These are proprietary connectors. Now, I'm going to stop holding my hands up here because it's getting a bit awkward. Bring you back into focus. Yeah, so these are proprietary connectors made by different companies. So MC is made by a company called Straube. They used to be made by Multicontact. That's where the MC came from. But now made by a company from Austria called Straube. And they have a patent on their particular plug and socket design. So surprisingly, those pins go this way around. That's the male, that's the female, and that's the pins that go inside them. Push them in from the back. And the mating of those is very precise in terms of the amount of pressure that they exert when they're mated together. And that's very important in terms of the reliability of the connection. Whereas this brand here, with its own pins and sockets, is probably perfectly okay. But what you can't do is mix and match them. And it's in the standard. It says a plug and socket connection, it's in 5033, must be same type, same brand, both sides of a connection. And I've personally had, before this was a requirement, by the way, I personally had a failure, which is I didn't know about this problem, and it wasn't a requirement in the standards, and we had mismatched plug and sockets connections, and I noticed that the array wasn't working, and I sort of wiggled a cable by accident, and it started working, and I wiggled it, and it stopped working. That's not a good look. That meant that the tolerances of these pins was not the same, and so there was a loose male pin in a larger female socket, and it was basically arcing inside there when I wiggled it. So there you go. Don't do that. Now, I do have an example of what happens when you disobey this requirement, and let's have a little look. Here we go. Just going to bring that one up for you. And it's Keynote. There we go. All right. So what you're looking at here is a little case study that I wrote for a failure of some plug and sockets. And that I didn't get involved in this, so it was reported to me by one of the lines companies, or as they call them in New Zealand, or DNSPs as we call them in Australia, in New South Wales. And so the story behind this one is that the customer had, for its time, quite a big system. This is from 2010. They had 2 inverters and two kilowatt arrays installed, and the customer was paying around $200 a quarter for electricity. So they got their first quarter bill after having the solar installed, and it was $1,200. So their bill went up sixfold after installing solar to save them money. What? So they basically complained first to the installation company, and one of the things they said to the installation company is one of the inverters has a red light on it day and night, and it's a bit hot to touch. Well, there's a bit of a concern. So the installation company swapped out the inverter at the end of a day, probably when the sun had gone down, and then went away. And so next day, still that inverter was hot to touch and had a red light on it, but the customer didn't really know what that meant. So it's not a very educated customer. Anyway, they complained to their electricity supplier, and eventually a technician was sent out from the utility to inspect the system. And this is how they found the configuration. So 2 inverters, 2 arrays connected to a common switchboard, and the sequence of events, I just mentioned that, but I'll skip over that sequence. And the utility noticed that there was 66 kilowatt hours per day being consumed on the export register. So in New South Wales at the time, you got a separate solar meter being installed, which was to export all of your solar and earn a very healthy amount, 60 cents a kilowatt hour back then. But instead of exporting, it was importing. So how can a solar meter import energy when it's only connected to a solar inverter, nothing else? So they got their meters out and measured stuff, and this is what they found. So they found that one of the inverters was actually passing AC up to the roof, and it was 13 amps was coming from the grid to the AC output of the inverter. So it was consuming 13 amps of grid power. And when they measured the DC cables, they found 2 amps AC and 11 amps AC, respectively, on the positive and negative conductors. That is very, very bad. Okay, so effectively the inverter was a pass-through device, passing current up onto the roof. Now, you might wonder, how did it make a return path? Well, it turned out there was a bit of a problem on the roof. The plug-in sockets had basically destroyed themselves. It arced onto the roof and burnt holes in the roof, and therefore you had a short from the PV array cables to the metal roof, and the metal roof had a hot water service connected to it, rooftop hot water, which had a equal potential bond on it, protective earth bond on it, and so was the return path going back through the earth conductor. So it was pretty bad, and it wasn't just one spot. There were several spots where this problem was either had occurred or was about to occur. Now, what caused it, I can't be 100% sure because I wasn't there, but I suspect it was either a poor quality plug-in socket, poorly installed, i.e. the cables are lying on the roof, and this is a salt-rich environment, 100 metres from the ocean, and maybe they hadn't even been pushed in properly. You actually have to push them in together until they go click. If they don't go click, then the seal hasn't been made properly. Or the gland on the rear, so if I just point you the gland on the rear here, if that hasn't been tightened up properly, when you tighten this, it compresses a rubber seal around the cable. If you haven't tightened it properly, then water will track into inside this connector, and being salty, rich environment, corrode it. So there you go. That was the result of a failure of a plug-in socket. And you might ask, well, surely the inverter should have shut down when that occurred. The inverters are only tested for 300 milliamps of earth leakage. When you get what's called a bolted earth fault, so like that one you just saw then, it's going to be pretty damaging. The inverter basically blows up and becomes a load instead of a generator. So this customer was consuming 66 kilowatt hours a day from their inverter, heating up some cables and heating up their earth conductor in their switchboard. Whoa. So that system was basically arcing onto the roof day and night. By night, AC. By day, AC and DC. Sounds like dirty deeds done dirt cheap, if you ask me. There you go. All right, so we've come to the end for today. Thanks, everyone, for watching once again. Just a couple of last-minute notes here. I've got my next Toolbox TikTok again the next Sunday, the 5th of January at 1 p.m. And so feel free to chime in. Also, check out my channel. You're actually watching it now, but there's a whole lot of content on my YouTube channel, The Smart Energy Lab. So please feel free to dip in there and have a look around. And I love getting questions from my audience. It sometimes takes me a week and wanted to answer them all. So feel free to email me a question. I just realised I better type my email address in there for you. So there we go, glenn@solerequip.com.au. Just send me an email if you've got any questions and any suggestions for future Toolbox Tech Talks. So I'd like to make sure that this is content's relevant for you. So yeah, thanks everyone. And g'day Ray. Yeah, you're becoming a regular. That's good to see. So yeah, I'm going to just wrap it with a few tunes and we'll see you again next week.
I don't need to analyze every word that comes out is a lie. Make it look like it's so ice. You won't make it to the finish line. Now if you gotta know the truth was gonna let you go. You was fine, never mind, unpredictable. Feet high off the ground, you ain't no one. You a star, blow it up like supernova. In the nighttime, hit my hotline. Sharing secrets, you wish really was part your life. Basic bullets, with my bullets. Does your wifey know you're begging for my notice? Promise you're the same, running for the meds. Show you like my vibe, pass my candy on my